just quickly recapping this idea from yesterday, the crux behind what we should have learnt yesterday is that if the population proportion is unknown, then we can use what we call a confidence interval to try and predict what it might be, or certainly a range of values. And really that's the point. Where that interval comes from, it depends on the level of confidence. And so 95% was the one we focused on yesterday, but really it can be any percentage. The higher the level of confidence, the wider the interval, so that you've got more chance of capturing the population proportion in your interval. Like I said, we focused on the 95% level, but there is certainly you could get any percentage. 95, 99 and 90 are the three most common. And so to calculate the interval, you have got this not particularly nice formula, and we'll formalise that or generalise that today. But to calculate that interval, it is based on the sample proportion and the sample standard deviation. And that standard deviation is then multiplied by some Z value. That Z value is linked to the level of confidence. So yesterday we were focusing on that 1.96 because that links to the 95% level of confidence. But that could change. So what changes obviously is your proportion, your N value, and your level of confidence. But the idea is you get this interval, which we would often write as just in a bracket like this, in which we would be at a certain level of confidence capturing that population proportion. And so then the interpretation is, if we repeat this and we have a lot of samples, then 95 in every 100 samples should be capturing that population proportion. We will be out slightly, like the idea is, well, 5% of samples will most likely not. So really today it's just practicing that idea of determining the interval and how we get the values that are associated with it. And here we've got the 95% confidence interval. Where does that come from? Our values, the Z values, they are just your standardised scores for those that centred 90%. So I just want to show you on your calculator where it comes from, if I can call it up.
Sorry, I know you probably went over this in past few lessons, but I haven't actually pulled up yet. But for all of the sampling stuff, do you just treat everything as normal distributions?
So yes, if we've got to make sure that N is large enough, so N's got to be greater than or equal to 30, we've got to satisfy those three criteria, yeah. NP, but otherwise, yes, by the central limit theorem, we make that assumption. And that is the basis behind everything that we do from then on. Okay, so if we go centre-tail setting, just to show you, probability of 0.9, the standard scores are associated with that. And you can see there's your negative 1.645 and 1.645. So at the 90% confidence level, they're the Z scores that we would be using. And you can see that from the diagram, those A and B values. At the 99% level, so if we went back, you can try this yourself if you like, 0.99 is what we would put, and they're the Z scores that we would be using. So the negative 2.576, etc. And of course, the one we did yesterday at the 95% level, this is the reason why we were using 1.96 and negative 1.96. All right, so as long as the sample is large enough, as long as it satisfies the criteria with your NP and N times 1 take P, both have to be greater than or equal to 10, we can use the central limit theorem to approximate the normal distribution with the mean equal to the population proportion. And so from that, we can have a certain level of confidence depending on the whatever that is. So in the first one, 90% confident that the population proportion is within however many standard deviations of the sample proportion. So in this case at 90% it's 1.645. 95%, like we did yesterday, was the 1.96 standard deviations from that sample proportion, and 99% 2.576. So as you can see, as we increase the level of confidence, the number of standard deviations from that sample proportion increases, and that increases the interval width because we want to be more confident of capturing that population proportion. So they are the most common. However, we could do any. And there is an E-activity actually that tells us what the Z-score is for that particular level of confidence. So I gave you those E-activities last time. So you can use the E-activity, or because in all, sometimes things break down, and if something's going to go wrong, it'll be the E-activity in your calculator. You can always do what I just did. Use your centre tail setting and put in. So let's say we wanted an 80% confidence interval, 0.8. Just use your standard normal distribution. And if we go next, they're the two Z values associated with that level of confidence. But just to show you how it works with your E-activity, if it would like me to get in, and just going in to that. Why is that not working? Okay, I've lost my E-activity, so I'll have to show you that next time. Of what we've already done. But just to repeat, just to remind you, we just make the assumption, as long as n is large enough, etc., that we have a normal distribution with those sample proportions. But remember, they are distinct values. Hence the reason why it is an assumption, right? But they are distinct values, and we just use that normal distribution to approximate the proportions. And then to get the interval estimate, that is the general. So yesterday we did the one with Z is 1.96, but this is the general interval. So we are trying to capture the population proportion in between two values. And we use this when we don't know the population proportion. And so what will change, obviously, is your Z value dependent on the level of confidence. And then the sample proportion will depend on your sample. Sometimes it's written, like I said, as two values. So rather than the inequality, just as two values in a bracket, usually square, but some books will do, the circular brackets. That's not important to worry about the distinction between them. All right, so the interpretation, the most important interpretation to recognise, it's not a probability. So you can't say there's a 95% chance of capturing the population proportion. That is a very bad interpretation. You cannot say that. What we can say is at a certain level of confidence, we can make the assumption that the true proportion lies within that interval. But what's more important to say is that if we construct many intervals at that level of confidence, we would expect, in this case, if it's 95%, we would expect 95% of them to capture the population proportion. So that's the best interpretation of the confidence interval. It is not a probability. That is important to make that distinction. All right, so let's do it. So you need to go to interval. So in your stat mode, you will see we're familiar with distribution and inverse distribution. So you need to go to interval. And it is a one proportion Z interval. So those of you that do specialists, there is the other one as well. So one proportion Z interval, and then hit next and type in your confidence level as a decimal. So in this case, it's 0.95. Now the X is the number in the sample that have the attribute, and n is the number in the sample. So that's 30. So x is the number in the sample that have the attribute, which we don't actually have that here as it stands. But we can figure it out because we know 0.7 of the sample have the attribute. So it'd be 21. Yeah. So 30 times 0.7 is 21. So that's the only thing you've got to be careful of on the calculator. It wants that actually as a fraction. Well, kind of like how you would set it up as a fraction. 2130, hit next, and there you go. There are your two values.
Why are you typing it like 50?
It's 30. It's 30, sorry. It's a 3.
Sorry, can you go over that again?
Sure. So what we would normally do is set up our sample to say how many have the attribute. You've got this many over 30. Now, in this question, you're not told how many out of 30. You're just told that the sample proportion is 0.7. But your calculator wants you to put in that number, whatever that's your x value. So how do we find x? Well, we just do 0.7 times 30 because it's 21 out of 30 is what gives you the 0.7. So when we do it on the calculator, that x value is that what goes up there, 21 out of 30, to get your 0.7 in the first place. So often you're given that in a question, but you might not be, as in the case for this example. You're given 0.7 of the sample has the attribute, whatever it is that we're talking about here, something to do with primary school students who own a mobile phone. And so once we put in our level of confidence as a decimal, then put in that 21 on 30. Is that okay? Does that make sense as to why it's 21? 30 is the number in the sample. And then, oh gosh, I've lost it. There it is. So, and there's your lower end and upper end of the interval. You can check your p value. It's given there, 0.7. So that's a good way just to check it. And obviously n is as it is. So you can use that now. We just did one manually. I'm not going to do any more. Use that now to try example 2. And you also have the instructions here as well. There's also an E activity called CI for proportion. So I'll show you the E activities. I'll set those up and I'll show you them next time because they're not on my CAS at the moment. The best way to interpret this, and this diagram is really cool, because what it does is it shows you that the population proportion is fixed. That does not change. What's varying is the sample proportion. So that red dot is your sample proportion, and it's based on how many have that attribute in your sample. So this is showing you we've got 20 samples, and we would expect at the 95% confidence level that 19 out of 20, 95% of 20, captures the population proportion. And you can see all of them capture the population proportion except that one there. So they all capture that population proportion. So, the sample size has to be the same, obviously, for all samples, so that you've got that same interval width, because the standard deviation based on n, right, is based on n. And so what you can see here is even though we've got variations in our interval, all of them bar one captures that population proportion. And that's the point. So then we can conversely say, well, is this sample, if we know the population proportion, is this sample representative of the population? Well, maybe not. Or maybe this is the one out of 20 that actually won't capture the population proportion. Because remember, we would expect at the 95% level that 5% of the samples won't. So it's a cool little diagram to kind of visualise what's going on. Is there any questions about that? All right, let's try this next one. All right, what happens if we decrease the sample size? Let's say it was, instead of 184, 500, so that same proportion, let's say 92 on 250. What do you think might happen if that was your sample proportion? Would you get the same interval? You've got the same proportion, and if not, why not? And what would you expect?
A wider range.
A wider range? Why? Why would we expect a wider range?
Like one more person can change the proportion more. Like if you've got 1 over 2, that's 50%. If you have 50 over 100, that's like... Yeah, bigger sample, you're more sure.
Yes, with a larger sample, you're more sure, more confident. So yes, we would expect, yes, that one person, that variation of 1 or 2 people is bigger. It's a bigger percentage of the sample size compared to if the sample size was smaller. And we can prove that just using numbers. So let's do it. What if this was 92, out of 250? What would our interval be? Well, there it is. 0.3178, 0.14181 or 82. That is wider than this one. So questions will be asked about that. Like, I'm not even saying could. I will be asking those sorts of questions. If that was me anyway. But pretty confident, level of confidence that you would get that kind of understanding that is important. Because most students can calculate the interval, right? That's just a calculated job. But it's that interpretation that's important as well. And so they have in recent years been asking questions about that understanding. So things like increase the level of confidence, what happens to the interval width, or decrease the number in the sample, what happens to the interval width. And you can see that here it is wider because less in the sample means that you aren't as sure. One person variation has a higher percentage change than if you had a larger number in the sample. And I guess that's what the next questions are about. So let's see if you've actually been listening. Will a 95% be narrower or wider? It will be wider. Why? Because it's a higher level of confidence. So we are more confident.
Only in that when you say you're more confident, you're actually more unsure.
We're confident we're going to capture P, but the range in which P lies, yes, is bigger. That is quite true. Now, we already talked about the 100% confidence interval. So did we listen to that question as well? What 2 values will it lie? Well, 0 and 1, is that practical? Of course not. It's pointless. Obviously, it's got to be somewhere between 0 and 1. No matter what the attribute, the proportion will always be between 0 and 1. So it's actually a pointless exercise. Apologies for my poor writing. All right. Have we done number 4? So a sample of 200 adults showed that 34 regularly spent over $100 on food each week. Maybe I should change that to over $300 these days. Determine the 99% confidence interval. So I'm getting 0.1016 and 0.2384 as opposed to the 80%, which you would expect to be narrower, lower level of confidence. So